Hello and welcome back to Applied Advanced Calculus. My name is Nathaniel Posesorsky and today we are going to be looking at Divergence Theorem. Let's jump into it. So for Divergence Theorem, it states that the triple integral of divergent f dv is equal to the double integral of f n ds. That looks familiar, doesn't it? We saw it in a previous video. That's the flux. So if we were asked to evaluate the triple integral of divergent f dv, we simply do the flux. If we're asked to evaluate the flux, we simply do the triple integral of divergent f dv. And if we're asked to prove divergence theorem, you have to do both. Let's look at an example. Over here we are told to verify divergence theorem for the vector field and region f equals to 5x, 2z, 4y. And region x squared plus y squared is smaller or equal to 1. And z is between 0 and 7. So now we could tell just by looking at x squared plus y squared is equal to 1 that this is the equation of a cylinder of radius 1 pointing in the z direction. So we could plot it out over there in our graph. Then we want to find our normal for all three surfaces of the cylinder. So let's start with surface S2. For surface S2, your normal is going to be perpendicular to the surface going outwards. You can't have a normal going inward into your surface. And so the normal is just going to be going along the z direction. So it's going to have 0, 0, and 1. And you could see that its y component of that vector is equal to 0. So when we are going to do the dot product of the normal with f, we are going to get 4y, but since the y is equal to 0, fn is simply 0. And the same thing happens for S3. S3 is in fact just the negative value of what we find for S2. So in this case, it's still 0. Then, we know that it's a cylinder, so we could use cylindrical coordinates. So we're going to replace x by r cos theta, y by r sine theta, and z we're going to keep it as z. Afterwards, if we look at the S1 surface, we could see that the normal is going to be going everywhere, except the normal in z is going to be 0, since it's perpendicular to the z axis. So it's never going to be going along z. The normal is simply going to be cos theta, since the radius is 1 for the x value, sine theta, and 0. And then for our f vector, we are going to replace the x and the y's by cos theta and sine theta respectively. And the z, we're going to keep it as it is. And that gives us the new vector you see over here. Then, if we do the dot product, we change our dA to d theta dz, and we do the integral from 0 to 2 pi with respect to theta and 0 to 7 with respect to z, we get the following equation down below. We could then solve the integral, and we get a final answer afterwards for that integral of 35 pi. But the last step is to take what we found for surface 1, surface 2, and surface 3 and sum them up, which gives a final sum of 35 pi. However, we are not done because the question said to verify divergence theorem. So we did 1/2 of the problem. Now we are going to calculate the divergence of f. So if we do divergence of f, it's di p over di x plus di q over di y plus di r over di z, and that simply gives us 5. Then the triple integral of divergence f dv is simply going to be 5 times the triple integral of dv. And we know that the triple integral of dv is simply the volume. What's the volume for a cylinder? Well, it's pi r squared times h, r being 1, and h being the maximum z value, which was given at the beginning to be 7. So we could calculate the volume of the cylinder to be 7 pi, And then the triple integral of divergence f dv is going to be 5 times 7 pi, which is 35 pi. Since our answer of 35 pi is the same at the top and at the bottom, we just proved divergence theorem. So I hope this was helpful at better understanding divergence theorem. If so, please make sure to leave a like and subscribe, and I'll see you in the next video. Thank you.